Okay, so we proceed the description of the steps that we need to perform in order to de novo detect transcription factor binding sites. So this means to find substrings and sequences that are candidate for the binding of a transcription factor. So I have written here a small report that can be used, that can guide us for the detection of de novo transcription factor binding sites. So de novo here means that we don't know a priori what we're looking for, so we don't know the actual substring, but we're going to use a set of DNA sequences, as we will see later on, in order to firstly detect such transcription factor binding sites. And then the idea is that using these detected motifs, we will build a position-weight matrix, and with this position-weight matrix we will scan sequences to find out where a motif might be. So some glossary here. TFBS is a transcription factor binding site, and this is a DNA subsequence on which a protein may bind to. And usually these transcription factor binding sites are on the regulatory region of a gene, and this region usually it is a region, a genomic region upstream or before a gene that can regulate its expression levels. Okay, let's see what we have now and how to obtain what we don't have. So let's assume that we have a set of genes. In this example we will have 67 genes, and specifically we have the regulatory regions, which means some bases upstream a gene. So for 67 genes, gene 1, gene 2 and so on, we have these red here genomic regions. In this example the size of this region is 500 base pairs. Then we have another set, and now I must mention here that this data set of 67 genes comes from a specific pathway. And we should remember that the genes in a pathway, they should at least at some degree be able to be expressed more or less simultaneously in order to achieve the function of the pathway. So pathway means that we have interaction between genes, and in order to achieve a final function, these genes must be somehow concerted, their expression. Which means that here in the regulatory regions of the genes, we should be able to find some transcription factor binding sites where a protein can bind and regulate the expression of this gene. And we should find such a transcription factor binding sites more often than another random list of genes. So if this is a random list, we should find this small motif here, this blue guy here, more often than we find it here. So for example, it might be a result that here in the 67 genes we find this substring, a specific substring 400 times, just an extreme result, whereas in a random set of 1000 genes, so remember here we have 67 genes and we find these motifs 400 times, and here we have 1000 genes and we find this motif 100 times. Which means that we have a huge overrepresentation of these small sequences of this specific substring here compared to here. Okay, so how we can start? Now, in order to finish what I was saying before, we have the overrepresentation. This is a good candidate. This substring here is a good candidate for a transcription factor binding site. So then we can get all the sequences, find also other similar sequences here that do not differ so much from this one. So for example, if this one is A, C, C, T, G, C, then we will get all the instances of these sequences here, plus some other sequences, for example the A, G, C, C, T, G, C, that differ a little bit from this one. And based on all these instances, we will build a position-weight matrix, and then we will be able to scan all the 67 sequences with this position-weight matrix to get a score. The locations that correspond to the highest scores will be the ones that a transcription factor may bind. Okay, so the first step is to get some DNA regulatory sequences that belong to pathway. Now the easiest way is to use ensemble and a tool called Biomart. So let's go to the internet. So here in Google I write www.ensemble.org. I go here and then I click on the Biomart. So Biomart is an environment where I can have access to the data server of this ensemble. Now what I'm doing here is, let's go from the beginning. Let's go to a new one. Okay, so this is the page that you will see. And I choose the database, ensemble genes 109 is the latest version. Choose dataset, human genes. And now we go for the filter. So here we say that we will use the ensemble version 109 and we look for sequences related to human genes. And now we must apply some filters. So when we choose filters, we have these options here, and we will search, we will restrict our choices based on some gene names or some gene information. So we have several options here, and the most comfortable for us is the following: input external reference ID list. Now if we go here to the selection choices that we have, we may find these reactome IDs, and we'll choose it, and I will explain now what it is. So reactome is another database of pathways. So the idea is to find a pathway that we are interested in. In this example, I will choose glycolysis. I will get its ID from another website. It's here actually. I will put it here, and ensemble will give me all the genes related to this pathway. So I go to reactome. The way that I can find it, this information is the following. So if I type reactome and then the name of the pathway that I'm interested in, it's glycolysis. The first link in Google will give me the pathway, and the only thing that I need is this table identifier. I copy it, I go here, and now I have finished with the filtering. So this again, I repeat here that using this ID of the pathway, ensemble knows which genes comprise this pathway. Now from these genes, what I need is to get some specific attributes. So I go to the attributes here. I don't care about the protein structure or some features of the gene or homologs or variants, but I care about the sequences, because what I need to obtain is some basis upstream the specific 67 genes. So upstream means before the gene starts on the regulatory region of the gene. So I click here on sequences, and what I need to get is the flank of a gene. So this is the gene here with the boxes. Flank of the gene might mean either before the gene or after the gene. So what I need is flank, so that I need the upstream flank, and I click here upstream flank, and then I put here on the box how many bases I need to retrieve, and I need to retrieve 500 bases. Okay, and then I can click here on the header information. Remember, we said in the class that the FASTA sequences have an identification line which is represented by this greater than, and then here we expect to read the name of the sequence. Now this is what they call header here, and what I need to have in this header is just a gene stable ID and nothing else, and then I click everything else. Okay, so I'm ready to go. I click on the count button. I see that out of almost 70,000 total genes that I have in the human database, 67 of them belong to the pathway that I used, the glycolysis pathway. Then if I click results, I can go here. I select for the unique results only in order to avoid having duplications. And then I click go, and the dataset will be downloaded. Okay, I leave it here, and this is our foreground dataset. So it's a dataset that we will use for looking for motifs or for substrings that exist here more often than in another dataset. And this other dataset is the background dataset, and I will build it by first choosing to download all possible genes from here. So how to do that? I go again to filters, and I remove this. So here now I have applied no filter. I have the same attributes. I click again on count, and now I see that I have all the almost 70,000 genes. I go to the result. It will take some more time now, and then I click again go. So I have chosen unique results only. The format is FASTA. Everything will be sent to a file. I click go, and I can download it. If I remember well, this must be something like 40 megabytes. Okay, so this process is described also on these images here. You can follow them. And now what we will do then is the following. So here we are. So this the total data set, the data set that we will use for the background, we said that contains almost 70,000 genes. So for all the analysis that we will do below, this 70,000 genes is a bit too much for us because it will take too much time to analyze them. So what I suggest here is to just take a random subset of these 70,000 genes, so just take 1,000 sequences to speed up the calculations later on. And now this new random subset of this total background will be our background, okay? I will use this terminology again. Now the next step is to detect the here I must write substrings in the foreground that are overrepresented. So how we do that? First we must write a function that will read the foreground and will store it in some data structure in RAM. As a data structure here I choose a list called data. So I'm using an infinite loop here, so while this loop is true I read line by line the text. So this is the first line of the text, so this is one line at a time from the text using the function read lines with n equals to 1. So this will read just one line from the text and will store it in the variable line. If the length of the line is 0, which means that I have reached the end of the file, then I will break the loop and I will exit this loop from here. But if the length of this line is not 0, then I proceed here and I search for the pattern greater than. So remember that if a line starts with a greater than and then it has some name like that, for example, it means that this is the name of a sequence, and after this line, so here and here and here, there is the actual sequence. For example, there is a sequence A, C, C, T, A, C, G, T, and so on, up to here A, and then again there is C, 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 blah blah blah, up to here, and so on and so forth. So this sequence is not in a single line but is split in several lines. And what we are doing here is exactly to get all this information for the one sequence and convert it to a single line. So the first thing that I'm doing is that if I'm on this line here, I use the gsub function of R to get only this motif, this one here, and store it as a name. And then I initialize a list from this data list here. I initialize an element with the name and initialize it to empty. So the purpose of this thing here is gradually to put inside here this sequence. How to do that? So if I'm not in a line that starts with greater than, then here in the specific element of the data that is specified by the name, I just put the line. Now I use the function paste because of the following reason. If I'm in this line, in the first line, remember that I have initialized this data name to an empty string, so I say that this data name will be the empty string plus this sequence, which effectively will be this sequence here. But when I'm in the second line here, then I want to concatenate what I already have, which is the first sequence, with the second sequence. So after the second time that I will enter here in these cells, I will put this sequence, the second sequence here, the second line, at the end of the first line. So I will have a longer line like that, A, C, C, T, A, and so on. A, so this A is this A, then I will have C, 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 and so on. Then I will read the third line, and this will continue, and so on and so forth. And then I will just close the file that I opened to read, so this one, and I will exit the function. So I use the function getData then to read the file called glycolysis.fa. So this has the FASTA sequences that I downloaded from Ensemble, and I store it to the list data. Now I'm doing exactly the same for the background, and I finish with reading the files. The second step is to process these files, and I can do to process the files means, okay, find or get all substrings. Now this is a bit tricky here. What I'm doing actually is let's assume that I have this sequence here, and let's suppose that we call this function with length equals to 4. You will see later on that the length that I'm using is 10, but just let me explain what this function is doing, assuming that the length is 4. So I'm doing the following. First, I use sapply. You must imagine that this is like a for loop that will run so many times as the elements in this sec list. So remember that this sec list is a list in R that has so many elements as sequences I had before. So for example, the first element might be it's this is the list of a name, and the value of this thing here, how we have called it, actually it's the data. So this is the data. Let's put data here, and the value of this thing is a sequence like that. And for the foreground, I have 67 such elements in this data list. Now, for each one of these 67 elements, I apply this function here, from here to this point. So apply and all the functions of the same family, which are the sapply, the lapply, and the apply, repeat some function on a data structure like a list or an array or a matrix and so on. And here the function that I repeat, I have the right to write it inside the sapply immediately. So let's see what this function is doing. This function takes a single argument, this I argument here, and this I is an element of the sec list. So the idea is to repeat this function for each element of this sec list. And I call each element of this sec list as I. So I here is an element from sec list. And this, since sec list will be our data, so an element from the sec list might be exactly this one. And its value of this one is this sequence here. Okay, so for each sequence, in fact, what I'm doing is that so this is a sequence now. I split it using a no separator, so it will be split in letters and it will create a vector like that here. But since it will actually create a list, up to here this will be a list. It will be a list that contains only one element, and this element is a vector, so that's why I use this double square bracket 1 in order to get this vector, and it will be this vector here. So this string split in elements. And what I'm doing then is the following. I use again the sapply, another sapply, and I say for each, so sapply now will be another function that will be applied on these elements here, and these elements are all the numbers between 1 and the length of this minus the length of the motif, which I said it will be 4, plus 1, and it will start from 1 and it will finish to this number here. So for each one of these elements, so for the numbers 1, 2, 3 and so on, so all these numbers are actually these numbers here, I will apply this function, and every time this j will take a value from these numbers. So what this function is doing, it will paste, so it will concatenate these elements together in a string. So when j is 1, the first element, this will be v of 1 up to 1 plus 4, 5 minus 1, 4. So it will be from 1 to 4. 1 to 4 is 1, 2, 3, 4, these 4 elements, and it will take these 4 elements and it will make a string out of them, this string. And this is the first motif here. And then it will go to the second element here, so this 2. So then this j will be 2, and what it will do here, it will be v of 2 this will be 2 here, and this will be 2 plus 4, 6 minus 1, 5. So it will be from 2 to 3, 4, 5, this guy. It will concatenate it to a string, CCT, CCTT, and it will store it, and then it will make J3 and so on and so forth. When this function will finish, this function, this is apply, it will return all these substrings as a new vector, where the first element of the vector will be this one, the second will be this one, the third will be the third substring, and so on and so forth. So this will be returned by this function, and since this external supply will run for all sequences, this x here will be the set of 4 possible substrings from all the sequences. So it will be these, the third, the fourth, and so on, and then it will be again here from the second sequence all the substrings, and so on and so forth. And then I take these results here and I use them with the function table. And the function table, what it's doing is that it will count how many times I have each substring. For example, it might find here, and let's say that from this sequence it will find also 1 time, and so on and so forth. It will find that the element CGTA is found 3 times. So the result of a table will be a vector let's put another element just to understand it. Let's say that the ACCT is found 4 times. So it will be a vector of these numbers, 3, 4, and so on, but it will be a named vector. So this 3 will have a name, and it will be this element. So what this function will return, it will return a vector where in the element called CGTA, it will have the value 3. So this function counts the number, the multiplicity of all possible different substrings that I find here in all sequences. So I do that for the foreground here, and of course we must do the same for the background. Now in this example I have used as motif length 10, so you must do the same, or you must choose another number if we say so. Now the next step is what we explained in the class, to use the hypergeometric distribution to find all motifs. So the goal of this is to find all substrings. Sorry, I use the term motif as substring, meaning the same thing. Find all substrings in the foreground that are overrepresented compared to the background. Now this is not so difficult because we have used the previous process sequence function that counts every motif here, and will count also all the motifs in the background. So I wrote this function to do that, and this function will create a vector of probabilities eventually, that now in the beginning is still empty, and for every element in the foreground here it will test if the name I of the foreground exists in the background, in the names of the background. If it exists, so if this if is correct, then it will just get the counts from the background dataset and will store it in the b counts here, in the variable b counts. Let's say that this is the number 30. Now from the foreground we also have the numbers of this motif I here in the foreground, and let's say that this is 20. So in the foreground we found it 20 times, in the background we found it 30 times. But the size of the foreground is, let's say, 1000 substrings, whereas the size of the background is, let's say, 10,000 substrings in the background. So now it's easy to calculate the hypergeometric probability, which would be this, the number of elements that we find in the foreground for the Q. The M, as we explained in the class, is the number of white balls in the background, and it will just be this number here. The N is the number of black balls in the background. It will be the set, the total size of the background minus the white balls. And K is how many substrings in total I had in the foreground, and it will just be this number that we have previously calculated. And we put here lower tail is on equals to false, because we are interested in cases that in the background we find more or equal number of such elements, so to estimate this probability. Okay, this number is prob now here, and I store it in the I position of the probes vector. Now the cells here, I just put it for the following reason. It is possible that a motif is found in the foreground but not in the background, since the background is a random subset of the whole genes. Now, having a motif in the foreground but not in the background will result in an error, and that's why I said, okay, let's assume that even if we didn't find it in the background, that we have found it one time. And I do the same thing. So I store the probabilities, I sort them from the so this means that it's increasing from the smallest to the greatest value, and then I can get the substring with the lowest p-value, which will be the first string that will be returned from this function. So the substring with the lowest p-value is the substring that is, let's say, more overrepresented in the foreground compared to the background. And then I find all substrings that are exactly the same or similar to this sequence. So similar means Hamming distance smaller or equal than 2 to this best sequence here. In order to do that, I use a library called string_dist, and I just wrote a function here that will get a candidate. For example, my best string is the CTG, just as an example. It will take all the foreground and it will take the threshold for the Hamming distance. This will be the number 2, as we said here. Let's see, I use smaller, so it will be the number 3. So I need less than 3. Okay, so I get the names from the foreground. Remember that all names are, the names of the foreground are strings, substrings, and the values of the foreground is how many times we find each fourth string. So for example, just to remind you what's happening here, an element from the foreground is this one, ACG TCTG, for example, and has a value 10, which means this is the name here and this is the value, and the name defines a substring and the value defines how many times we found it. Okay, so what I'm doing is that for this candidate, for this substring, I compare it with all possible names in terms of Hamming distance. And if the distance between the candidate and the name is less than the threshold is 3 here, then I get this element, this all names to I. How many times? As many times as there are in the foreground. So here, for example, 10 times. And I build a candidate list of substrings that will be used to build the position weight matrix. On the next step, we have done it in the class recently. From all these motifs, from all these strings, to build the position weight matrix, we know how to do that. It's just 2 for loops here. It's pretty easy. And then we can use a library called secLogo in R to build the sequence logo in order to see what the motif is, and this is what we get. This means that in the first position more often we have an A and then a G and then a C, and the higher the letter is, the more often we find it. So here, for example, in the second position, we find most of the times an A and sometimes a G. Also here in the last position, we find most of the times a C, the vast majority, and then a G. But here, for example, the probabilities of G and C are not so different, and that's why this G is smaller. Okay, then we can use the position weight matrix to scan the foreground and obtain a score for each position of the foreground. Also, we have seen that in the class. So I wrote a small function here that can be used to scan, to split the sequence into characters and then scan it to get a score for each position. Now, we said in the class previously that normally what we should do is to statistically define the threshold for the score of a position weight matrix. Here, just to make things simpler, I use a score as a threshold, the number 3. So I apply in all sequences this position weight matrix to get scores. So the result of this with the S-apply and the transpose will be a matrix comprised of scores which be the score of position weight matrix in the respective position of the sequence. And what I'm doing then is that from these scores I create another matrix which will have true or false, and it will have true only if this requirement is fulfilled. Why I'm doing that is because I can now use the function heatmap in order somehow to visualize this result. And let's see if this is possible. Cancel this, and I go here to RStudio, and I can run this function. They get this result. So this the red is the false, and the small dots here is the true, which means that in this first sequence I have 1, 2, 3, 4, 5 instances of the position weight matrix with score more than 3, and so on and so forth. So this is a result that we got here, where on these 500 base pairs of each sequence we find a match of the position weight matrix greater than 3. And now this is actually a de novo discovery of a motif, because when we started with the FASTA sequences we didn't have any idea for what motif we are looking for. We used the dataset itself, we're comparing the foreground with the background, first to find the interesting substrings, and to build a position weight matrix and scan the sequences using this position weight matrix. So that's all. Thank you very much.